This is my first time presenting under a roof without missing a pose, so please understand if I'm nervous. Okay, good morning everyone. Today I'm going to tell you about Autobahn, which is a tool we made to infer strictness annotations for Haskell programs using genetic algorithms. And before we see the tool itself, let's think about a problem. As we all know, Haskell is a lazy language, and then laziness can have unexpected costs. On one hand, if we have a program that's too lazy, it might suffer from performance bugs like thunk leaks. And on the other hand, if we have a program that's too strict, not lazy enough, the program will waste time in computation that's not necessary. And at this point, you might think, why can't the programmer just look at package and then find a good library that's optimized by some experts? So it's not that easy because the library writers cannot always predict how lazy or how strict their library should be without knowing how their library are used. So there are currently two major methods to deal with the laziness problem. And then on the left, we have GSC compiler optimizations, which perform some kind of strictness analysis and then try to tune the laziness of the program at compile time. And on the other hand, Haskell also allows programmers to insert strictness annotations, also known as banks, by hand, so that they can tell the program, okay, at this point, please evaluate the expressions strictly, don't create thunks. So these are not very satisfying because on one hand, we have the compiler, which has to be sound on all possible inputs. So there might be some input that will change some behavior. For example, introduce non-termination if we add a bang, but not on all inputs. Whereas Haskell, Haskell compiler only explores the banks that are absolutely safe and might be able to improve performance. And on the other side, we see the same picture. Right, I forgot to explain. So this is a universe of all possible banks. One can insert to one specific program, and then the red circle over here are the banks that actually improve performance. So either be it less memory usage, shorter runtime, and on the left-hand side, you see the little blue circle, which is the banks that once added to the program, it never introduced any non-termination on any possible input. There's a larger purple circle that has the banks that might introduce some non-termination, but only on those input that the programmer doesn't care about. And we can see that this is the banks some programmer can add. So you see it's all over the place. They might be really bad luck that it doesn't make it faster, and it's just looping all the time on everything. And you see that it might be safe, but then for the inputs that the program actually cares about, it doesn't even terminate it. Right, so here is an example of the difficulty of adding annotations by hand. So on the left-hand side, we see a program I found from Stack Overflow, which is the important part of this program is a function called upgrader thread. And it takes a mutable channel, and it will try to recursively update this mutable channel for any iterations. So at the base case, you see that it will read the list of integers from the channel and then print it out. For each recursive step, first it will read out the list from mutable channel, stores it in vlist, and then it calls a transform function that completely evaluates this vlist, as we see here, and then stores the result in rest list. And finally, it puts this result back into the mutable channel, and then calls recursion. And here we see the heap profile this program produces. And we can see that it's leaking memory because we would expect the only object on the heap should be the list itself and the integers in the list. And you can see the paper for detailed stripes that breaks down this heap. So this programmer was desperate, so she searched online and then found this guy's answer. Usual cure is to force search evaluation on the accumulating parameter, which is here on recursive programs. And she looks like this guy, all the medals and all the hair, so pretty credible, right? So she added a bang before the chain bar, which didn't work. And then it makes sense because the program is calling take n bar on the argument anyways, so adding bang doesn't contribute anything. So actually the important one is actually before rest list, because this bang will trigger the call to transform, which will completely evaluate the v-list in the mutable channel. And then in fact, we see the heap's gone, or most of it is gone, right? So here, from that example, we see the challenge of adding annotations by hand. And here is where Autobahn comes in to help. So it uses a machine learning algorithm for optimization called genetic algorithms to try to look at the source file and then infer good places to add certain annotations. And this algorithm is really simple. It's modeled after the natural selection and evolution. So you have things you want to make better. And then each thing is represented by some chromosome. And inside this chromosome, you have genes encoding the properties of this thing. So I will just jump into our representation of the algorithm. So here you see each place where you could or could not have a certain annotation is a gene. And then this is a complete program. All the places you can add a bang is one chromosome. And then here you can see that this program has a bang in the first possible place and two bangs in the middle, right? Genes and chromosomes. And then for each program, the user can choose one of these metrics, be it runtime, GC time, or allocation, and then we'll assign a score to the chromosome. And in this talk, I will consistently use lower performance score is better, and also in the later graphs. And we'll also time out programs that run twice as long as the original unoptimized program to prevent non-terminating program to get into future generations, right? And then so here you see that many chromosomes together form one generation. And then to introduce new chromosomes, we have two possible ways. One is mutation that picks certain genes in one chromosome and then change them into the other genes. We have crossover, which takes two chromosomes and then pick genes from either of them, combine them into a new chromosome, which is crossover. And lastly, we have this selection function that tries to pick the better chromosomes within a generation and let them survive onto the next one. So this process, we'll repeat this process until we get a satisfying generation or until time runs out, right? So to set up this algorithm, we need some very simple configuration. And these are some simple inputs. Autobahn needs to know the complete source file, where it's located, and then how to compile it. Right now, we're just calling cabal, and then which will look for the cabal file in the project. And then it needs to ask the programmer for which metric he or she wants to optimize on. And then it also asks for a subset of this entire project where performance matter. And this is helpful because Autobahn can then focus only on this portion to make the program faster. And also, the programmer can protect the rest of the program by not supplying them, because maybe in the rest of the program, if you if you add a bang, it might introduce non-termination. And then here's a allotted time for Autobahn to run the optimization. And it's very important to supply representative input to the program you want to run, if any. And then we'll see a reason for that later. So, and right, actually we still run that for that right now. So here we have a program, and then we see that factorial takes a natural number. And then, as everyone knows, factorial will diverge on negative numbers. So we see, GAC compiler wouldn't add a bang before X because it knows that if G is caught on a factorial that diverges, that will be a problem. That introduces non-termination. However, if the programmer doesn't care about negative numbers being passed through factorial, then it makes sense for Autobahn to add a bang before X because it's gonna print out anyways. So here again, we see the advantage of Autobahn on top of the compiler is exactly that it tries to explore this larger place of possible bangs that might introduce non-termination on some inputs, but the programmer doesn't really care about that part of input. And here we have some numbers about the performance of Autobahn optimizations and Autobahn itself. First is a case study using a program called garbage collection simulator. So on this graph, on the horizontal axis, you see different inputs, and it's actually portions of the same trace fed to the garbage collection. And then we see that here, you have the full trace, half trace, third trace, and then this is 1/15th, which is the trace that Autobahn is trained on. And on the vertical axis, you see the runtime normalized to the original performance of the program, annotated. And here we can see that black bar means manual annotation written by the original author of the program, and then red bar are the automation produced by Autobahn. So as you see that across the bars, we have optimization always making the program faster. And then most of the time, Autobahn optimization is competitive with the hand annotation. And in the second case study, we used the async parser library found on Hackage, and it's slightly different. So the x-axis is still 4 different inputs, but of similar size. And y-axis, we still have the runtime normalized to bear, but it's important because we're using a library. So we wrote two driver programs for the library, and one only validates the input is a valid JSON file. The other will completely convert this input JSON file to Haskell values. So as you can imagine, the valid program should try not to evaluate too much, so it needs more laziness, and it needs fewer bangs. On the other hand, the convert program, because it's going to evaluate the values anyway, so it needs more bangs and be more strict. And in fact, we can see that when giving the wrong laziness, wrong soundness setting, Autobahn can both add and remove bangs to make the program faster. And then here we have some numbers, some more numbers on the stability of the Autobahn optimization. So again, this is 10 different inputs, and the y-axis is the runtime normalized to bear. And then by bear, I mean the annotated program. So here we perform a tenfold evaluation, which means that we train Autobahn in one of these inputs, and then you see there are 9 different dots for each input. So each dot is the evaluation on the input that it was not trained on. And then we can see across the picture, we're getting a consistent improvement of the optimization. Right. So here we have some number for the performance of Autobahn itself, and then we think this performance is acceptable because if the programmer starts Autobahn and then goes to sleep, and they will wake up the next morning and see some suggestions for annotations. And there's also plenty room for improvement. For example, we can parallelize the finished runs so that each generation will finish in way shorter time. And then we can also use GC API to instrument the annotations so that we can avoid interacting with the file system, the overhead of that. So finally, we also compare Autobahn to the recent development of Strict Haskell. Here you see that these are the programs we took from the no-fit benchmark and sorted by number of lines in the source code. And then vertical axis is, again, runtime normalized to original. And one thing to note is that although it didn't get that much faster, because those programs are very small and they're not really the target of Autobahn, but at least Autobahn preserves is at least as fast as the original one. And here we see the Strict Haskell pragma turned on. So black bars means they either produce an error or just went into a possible infinite loop. And then we see that there are a couple of places where the program became much slower than the original one. So here, again, Autobahn optimization has the advantage of never getting worse than the original. And it also preserves semantics, tries to preserve semantics on the as long as given representative input. Right. And then so there is plenty of work on static analysis, and which resulted in the cardinality analysis in GEC that I mentioned earlier. And then specifically, there's also this stingy evaluation, which at runtime try to evaluate an expression. And if it takes too long, it will just fall back to lazy. But turns out that was too complex to include the production GAC. So we're not using that right now. And then there's also a related problem by Chan Lessing that tries to add laziness to strict programs. But they're dealing with a different problem, and then adding laziness will not introduce non-termination. So thank you. And at this point, I hope you will want to use Autobahn because it gives some good improvements in reasonable time, and then it's pretty easy to configure. It takes some pretty intuitive inputs, and then it tries to protect safety once given representative input. And then thanks to my co-author Dio, who was awake at 3 a.m. this morning, Autobahn is available here. And thank you.
We have some time for questions.
Okay, so genetic algorithms seem to be a good fit for this because of the way the chromosomes fit to kind of the shape of a program. But did you try some of the more basic machine learning techniques like hill climbing? Because sometimes the generations required for genetic algorithms are pretty costly, right? So
yeah, exactly. So it's future work, and then we are exploring. At least our one of the actually the author of the GC simulator is experimenting with the hill climbing algorithm. So once we get more number on that, there should be better reports. Yes.
Hi, Eric Crockett. On all your examples, you were adding strictness annotations to like functions, but I was wondering if you had looked at strictness annotations in data constructors.
Right. That's also good point because adding annotation to bound patterns can't always achieve the same effect as adding strict fields to data constructors. So we think that shouldn't be that complex, and then we're exploring that as well as adding annotations, adding strict applications to functions, which will try to eliminate the thunk as add creation rather than add evaluation.
Hello, I'm Matthias again. One question, like, have you looked at how dependent the different sites are you can add strictness annotations? I assume there are not too many dependencies because that's basically when genetic algorithms work. Okay, I guess you looked at it. One very small question, that's just a yes, no. Does it make sense to think of that you can approach adding strictness annotation as a JIT, like while you're running the program?
Sorry, can you say again?
Does it make sense to see it as a just-in-time step you could do? Like, I guess somebody mentioned dynamic information.
I haven't thought about that, but yeah, again, so if we try to put that into compile time, we should guarantee soundness.
That's why I was asking about
runtime,
and then you do it when you have more information, if that's possible or maybe not.
Right. I think for compilation, we'll need more soundness than we have right now.
Yeah,
yes.
Yeah, definitely.
So one really nice thing about this is that once Autobahn's done, it just says, if I were you, I would consider putting a bang here, here, and here, right? And then you don't need Autobahn anymore. And indeed, you could regard it as a sort of attention focusing device that says, you, the programmer, go and look and see on all the inputs that you have in mind, would bangs there be good, right? So there's a human in the loop, and that's a feature, right?
Mm-hmm. Right.
So do you give the human any help? Like you might say, well, if you put, 50 bangs in your programs, that would be good. But I'm thinking, oh dear, 50. Whereas if you told me, but these 3 are the ones that really make a difference, that would be really helpful, right? So you say the other 47, well, you could have them, you could not have them. On the whole, I would, but do you see what I mean?
Yeah, that's a good point.
So give me the derivatives.
Yeah, if there are too many points, or too many banks added, it's also way harder to reason about soundness.
Yeah.
So starting here, if everything goes right, my senior thesis is gonna try to shrink down the banks we add, and then we'll also highlight the banks that are dangerous.
Right. So you can do shrinking, like quick check, right?
That's possible.
You shrink them, and then you say this is worth 20%, that's worth 5%. Yeah. Okay.
Right.
That would be cool.
Yeah.
Hi, Gurgurdi here. So the safety of this hinges on how representative your test inputs are, right?
Yes,
so
exactly.
What has been your experience in how feasible that is to ensure that your test inputs are cover enough of your program that you won't get divergence? Right.
So as you saw in the showing up, it's not moving. In the tenfold evaluation, here. Right. So here we have just different inputs. They're not related to each other. And then if you see this pattern, then it's probably the inputs are similar to each other.
Yeah, but it could be that all 10 has been really well-designed test cases in this example. So.
Yeah, I agree. That's possible. Yes, but I think this is the method the machine learning community at least tries to evaluate the stability of automatizations. Yeah.
Hello, Thomas. Tober here.
Sorry, were you?
I was wondering why you went for the genetic algorithms in the first place. So there was a question about hill climbing, but then you have plenty of other options for optimization, like particles form optimization, only optimization, simulatic annealing, and so on. And there are none to have like a better convergence properties than genetic algorithms. So. Yeah,
exactly. So pretty simple. Genetic algorithm works well here, and then it has a property of if you add a bang here and then one here, so you have 2 chromosomes with different bangs. And as one speaker mentioned before, that it's possible that if you just combine these bangs, there's no complex dependencies, and you will just combine the effects of both bangs. And if not, it also doesn't get trapped in a local Autobahn because of the mutation function. So I agree that other algorithms might work as well, and then we're exploring that.
How large of programs have you been able to apply Autobahn to?
How large?
Like have you tried it on a compiler, for instance?
Right, so...
I say this out of naked self-interest.
Yeah. So the paper so you see the, let's see, this graph, which is all the programs from NoFib, and then the paper includes the number of lines here. So that detail is available, yes.
Okay. So not like GHC or something, or Idris, or...
Not yet.
Okay.
To follow on that question, could you splice or segment a larger program and run Autobahn on the individual parts in order to be able to tackle these larger programs?
Yeah, I don't see why not, because here in the inputs, we ask for the part of interest. So here, we are only allowing one source file right now, and I think it's simple to implement for multiple source files, yes.
Last question.
Ren Romano from Google. So one of the problems that I see is if you're trying to use this for libraries, where you're going to have multiple different programs. Is there any way to sort of consolidate and say, well, I have this file in my library that I want to optimize with respect to these 20 programs and their representative inputs? Or is it limited to just one executable file?
Well, I think a simple approach right now, you can just run a test case that combines the 20 programs together, and then you write your own fitness function and feed it to genetic algorithms. So you want to optimize that particular fitness function for those 20 programs.
Okay, let's thank Remy again.